Hi everybody, my name is Ashley Nazema and I'm presenting Physics Lab 1. In the lab, we are looking at the motion of an object in one direction at a constant velocity and how well its motion can be predicted using a computational model. This is important because computational models help predict the motion of objects that cannot be tested beforehand, such as sending a rocket into space. Therefore, it's important to study the real-life motion of objects in comparison to computational models. This was studied using a video that will be shown later in the presentation. In the video, the object is a rolling soccer ball. The relationship between the position of the ball and the time the ball is rolling represents the ball's velocity, and should be a straight line when plotted, since the velocity is constant. Since the velocity is constant, there is no acceleration, meaning the net force on the ball is known to be zero. Since the force, the ball's mass, and the initial velocity are known, a manipulation of Newton's second law of momentum, force equals mass times acceleration, is the best model to help predict the motion of the soccer ball. After the prediction has been computed, it will be compared to real-life observations to see how well Newton's second law can predict the motion of an object moving at a constant velocity. In the video, the rolling ball is the system, and the ground, air, and the rest of the room are the surroundings. The ball is moving at a constant speed. To be sure the speed of the ball was consistent throughout, the ball's motion starts being analyzed a few frames after it was initially pushed, and stops being analyzed a few frames before the ball stopped. As can be seen in the video, the axes are oriented in such a way that the ball is moving in the positive x direction. This was chosen because in real life, one cannot travel a negative distance. However, if the axes were reversed, the magnitude of the velocity would not change, but the velocity would become negative. After collecting data points from the video, such as the initial and final positions of the ball, here are the calculations that occurred in order to create the computational model. The average velocity was calculated by dividing the total distance traveled by the total change in time. This was then used as the initial velocity and plugged into Newton's second law, which just returned the same velocity since it's constant. The initial position was obtained from tracker. The rest of the variables were then plugged into the position formula to get the new position. These two steps were then computed iteratively in a code to model the motion of the soccer ball in real life. At the top, the equation for momentum can be seen. P equals mass times volume. Newton's second law multiplied by mass achieves the momentum principle. Looking at the principle, since the force is zero and the velocity stayed the same, so did the ball's momentum. All the previous equations were helpful in creating the code to make the computational model. A starter code was also provided. It is the code labeled original. This was then edited in order to better model the motion of the soccer ball in the video. It is the code labeled my code. First, the mass of the ball was changed to the soccer ball's mass, highlighted in yellow. Then the starting position of the ball was changed to match the starting position of the ball in the video, which can be seen in green. The velocity was also changed to the average velocity calculated. This can also be seen in green. Newton's second law was then used to update the velocity. This can be seen in turquoise. The net force of the ball was taken into account in the formula, as well as the ball's mass, which is different from the original code. The ball's position was determined using the position formula, seen in hot pink. As can be seen, the ball's velocity in delta t is also included in the position formula, unlike in the original code. This code was then able to create a model that predicts the ball's motion. This predicted motion was then graphed. As can be seen, the predicted line resembles the observed line. Neither line starts at zero, which is to be expected because the ball's motion starts being analyzed after the ball has traveled for a bit. However, just looking at the graph, the observed line is not as straight as the predicted line. It has a few small curves. This indicates the ball speed was not constant throughout. These discrepancies were likely caused by things the model could not account for, such as the ball having a slight deformity as it rolls, which causes it to change shape, which causes the ball's change in motion. Additionally, the ball was rolled on carpet, which, while looked flat, does have more friction than a smooth surface. In order to better study Newton's second law with the soccer ball, it would be better to get a brand new ball to limit the effect of deformities, and to roll it on a flat, smooth surface, such as a bowling alley, to limit the effect of friction. Despite all this data, it's not possible to say how many pushes and pulls are added together in this case. It's known that two forces are acting on the ball for sure: the force of gravity pushing the ball down, and the normal force pushing the ball up. However, there are other forces, such as friction, that were not accounted for. As such, it's not possible to determine the number of pushes and pulls added together. One can only know the total pushes and pulls equal zero. To conclude, this experiment showed that an object can have a net force of zero and still move. It simply means the object is moving at a constant velocity, which means there is no acceleration. However, the object continues to move because it keeps its momentum. This is why objects continue to move in life after the initial push has left. Therefore, this constant velocity allows for a computational model to extrapolate the motion of the ball. However, in life, unlike in models, there are several factors that exert small forces that cause an object's motion to change, which is why it's best to look at both models and real-life observations to truly study and understand a principle like the momentum principle, Newton's second law of momentum.